Hello, dear friends, in my last video we have completed unit number 6, that is corrosion or corrosion science. Now we'll be starting with unit number 5, spectroscopic techniques. Okay, and these videos I am making in this lockdown period where the regular classes are not going on. These videos I'm making topic wise will surely help you for your examination purpose. I am going as per the syllabus of SPPU University. Okay, so our topic is spectroscopic techniques. Okay, this is unit number 5. Now, what are these techniques? These are the techniques of analysis. Spectroscopic techniques, these are the techniques of analysis. These are the comparatively latest techniques of analysis. These techniques have some advantages over the traditional methods, isn't it? Or conventional methods of analysis. So what are the traditional methods of analysis? Of qualitative and quantitative estimation. Conventional methods were mainly chemical analysis. What goes in the chemical processes or chemical analysis? As we know, we suppose this is a sample we want to detect. We start with the color of the sample, state of the sample. In chemical analysis, we'll check the solubility of the sample. We may go for the flame test of the sample. It burns with a smoky flame, it burns with a sooty flame, right? Then we'll go for element detection, we'll go for functional group detection, we'll prepare the derivatives, we'll take the test of derivatives, we'll go for confirmative test, and so on. So many processes, so many tests we have to carry out. Lot of sample is required, lot of reagents are required, so many instruments and apparatus are required, lot of time is required. These are the drawbacks of these chemical methods. So these methods of analysis are now being replaced by spectroscopic methods of analysis. Okay, now these are of different types. In our syllabus it is just initial part of spectroscopy is there only your syllabus get completed. So what is the basic part of different spectroscopic method? Basic part is we allow the sample substance or we allow the molecule under analysis to interact with different types of light, to interact with different types of radiations. We allow the sample substance or the molecule to have interaction with the electromagnetic radiations or EMR. Okay, so that is the basic part. There is interaction of sample substance, maybe solid or liquid or gaseous sample, with these electromagnetic radiations or simple radiations or light. Okay, and because of this interaction or on these interactions, some changes are observed in the sample substance, isn't it? That we are recording. We will keep recording of the changes observed in the sample due to interaction of these different types of radiations with the sample. Okay, before going to that radiation, before going to the interaction, let us have some brief idea about electromagnetic radiations, isn't it? What are these electromagnetic radiations? These are the form of energy that oscillates in a space, okay, at a very high velocity, right? And it propagates in a space in the form of two components, right? One is the electrical component. So suppose this is a direction of propagation. This is the electric component moving like this, and this is a magnetic component. These two components oscillates in a space perpendicular to each other. One is going like this, one is going like this. They are perpendicular to each other and are perpendicular to the direction of propagation. A rough diagram I have shown. This is the wave going in this direction. Suppose it is x-axis, this is y-axis, and this is z-axis. This is one component going like this. So it is the electrical component. Suppose it is electrical component of the electromagnetic radiation, and we say this is a magnetic component. This is magnetic component. It has a dual nature. It shows wave as well as particle characteristics. We mainly concern with the wave nature of the electromagnetic radiation. So these are one component going like this in this manner. This is another component, magnetic component, going like this. This is perpendicular to the direction of propagation and it is perpendicular to each other. This is called as electromagnetic waves, and it moves with a very high velocity. That velocity is 3 into 10 raised to 8 meter per second. That is velocity of light. Now as we are studying some interaction of the sample substance with the radiations, we should know what is this radiation. Just I have given the idea, and what are the parameters with which the radiation can be explained. What are the parameters? First parameter is wavelength. First parameter of electromagnetic radiation is wavelength. If this is a wave, what is the wavelength? Wavelength is distance between these two. This is maxima or crest, maxima, and this is a minima, isn't it? Two successive maxima. This is called wavelength. Wavelength given in a notation lambda. What is the lambda? As you know, it is distance between two successive maxima or distance between two successive minima, crest or trough. That is given in the form of notation lambda. This is a wavelength, isn't it? And it is generally expressed in a nanometer. Nanometer, convenient unit of expressing wavelength is nanometer. 1 nanometer is 10 Armstrong unit, or it is 10 raised to minus 7 centimeter or 10 raised to minus 9 meters. That is called as nanometer, isn't it? What is the amplitude of the wave? This is called amplitude. This is the amplitude of the wave. It is a displacement of the wave above x-axis or displacement from x-axis. This is called amplitude of the wave, isn't it? Third parameter is energy of radiation. Energy of radiation is given by E is equal to h nu. H Planck constant and nu is a frequency of radiation, and we know that nu equal to c upon lambda. So E is equal to sc upon lambda. Energy of radiation is hc upon lambda, where h is a Planck constant, has some constant value, and c is the velocity of light, has some constant value. So we can say energy has inverse relation with lambda. Energy has inverse relation with lambda, isn't it? So the wavelength, so higher the wavelength, lesser is the energy, or shorter is the wavelength, higher is the energy of the wavelength. So it has a inverse relation, and similarly we can say this nu is also inversely proportional to wavelength, right? So E has direct relation with frequency and energy has inverse relation with wavelength. So this is the second parameter. Energy has inverse relation with wavelength. This is second parameter. Third parameter of this radiation is frequency of radiation. Fourth parameter is frequency, nu. What is that frequency? Frequency is number of, suppose this is a point, number of wavelength units passing through the given point. Frequency of radiation is number of wavelength units passing through a given point in a given time. Okay, nu, that is expressed in a hertz. It expressed in a 1 hertz. 1 hertz is equal to 1 cycle per second. 1 cycle per second. That is called frequency of radiation, isn't it? So these are the few parameters. Velocity of radiation is given by nu lambda. Velocity of radiation is given by velocity is equal to nu lambda. Frequency into wavelength, that will give the velocity of radiation. And wave number is, it is number of waves per centimeter in a vacuum. How many number of waves are there per centimeter in vacuum? That is called as a wave number, nu bar, isn't it? So these are the common parameters. These are the 5-6 parameters. With the help of that, we can express the electromagnetic radiation. So such type of radiation having electrical and magnetic component, we allow to interact with the sample substance, isn't it? Suppose this is my sample holder. Okay, one tube is there in which I am taking the sample like this. Okay, so in this method, in different spectroscopic technique, I am allowing my light. I am allowing, say, some light we express, suppose, in a wavelength. Radiation we are expressing in the form of, say, wavelength. We can express in the form of wave number. We can express in the form of energy. We can express in the form of frequency, and so on. Here we express that light in the form of lambda. So certain radiations we are allowing to interact. So in these methods, this is recorded. What is the interaction of different types of light with the sample? Okay, so suppose, let us take one simple case. After this initial part of electromagnetic radiation, let us go to the introduction again, or basic part of different spectroscopic method. Okay, now suppose this is my sample. Here I have taken the sample substance. Okay, some solution we have taken, right? So it is sample solution. Okay, and we allow the interaction of different radiations, different wavelength, lambda, to hit on the sample. Okay, suppose we will hit 200 nanometer wavelength. Okay, we will hit next 300 nanometer wavelength, and then 400 nanometer wavelength, and then 500 nanometer wavelength. Okay, roughly I am taking example, and so on. Suppose we have a sample substance. We are going for analysis of the sample, and will be for that purpose we allow the sample solution, sample substance, to have interaction with these 4 lights. First we'll hit 200 nanometer light on the sample, then we'll hit 300 nanometer on the sample, then 400, 500 and 600. Okay, now what happens? Suppose I am a sample. Let us say I am a sample, and these 5 tables are there in front of me. I have been given offer to eat 5 tables. Okay, even if I am getting it at free of cost, it is not necessary that I am going to consume all the 5 tables to equal extent, right? I have my capacity. First thing, I have my capacity as a sample, and second important part, I have my choice. These are the 5 different eatables, 5 different wavelength. So I will eat that food, I will eat that material to maximum extent that I like most, isn't it? Suppose I like this food, 500 nanometer, right? 4th food. So I will try to consume it to maximum extent. Why maximum extent? Because I know that this particular food is giving me maximum energy. So it is sweet atom. Among the 5, it is a sweet atom. And my assumption is that sweet is giving me maximum energy to carry out my metabolic activities, isn't it? Maybe talking like this, or maybe walking or running, or all my activities. So by absorbing this wavelength, certain changes are there in the sample, right? That changes are recorded in the form of a graph. Okay, suppose this is the absorbance. What is the absorbance? What part of the light is absorbed by this substance? The sample substance. Okay, part of light is, this is light, suppose, and it is 100 nanometer, 200, 300, 400, 500, 600, 700 and so on. So this is wavelength, lambda, isn't it? So by absorbing certain part of light or some part of light, second point, I am not consuming this food, I am consuming this to maximum. I may consume this to some extent, I may consume this to some extent, I may consume all other food to some minimum extent, isn't it? But one wavelength I am consuming to maximum extent. So basic part of spectroscopy is, some part of light is absorbed by the sample, okay, and some changes are there in the sample. These changes are recorded in the form of a graph, in the form of a spectrum, isn't it? So for this sample, say, one simplest form of spectrum may be like this. This is spectrum. The spectrum is coming like this, isn't it? What is the observation? This particular sample showing this type of graph of absorbance, how much light is absorbed, and this is the light. So this sample has absorbed this 200 nanometer to this extent. It has absorbed this, suppose 300 nanometer to this extent. It has absorbed 400 nanometer to this extent, but it has absorbed this 500 nanometer to maximum extent. It has absorbed this 500 nanometer to maximum extent. That 500 here is called as lambda max. That 500, we can say this is lambda max. What is lambda? It is wavelength, and max means maximum. It is a wavelength which is absorbed by the sample to maximum extent, is responsible for certain changes in the sample. Certain changes in the sample. This UV visible is a part, one part of your syllabus. This UV visible is mainly concerned, or it is also called as, this UV visible spectroscopy is also called as electronic spectroscopy. It is mainly responsible, or it is mainly concerned with electron transition, electron jumping from lower to higher energy level, isn't it? So if this is E1 energy level and this is E2 energy level in the one sample, okay, in second sample, suppose E1 is this one, E1 is here, this is E1 and this is E2, isn't it? So for sample A, for electron transition, electron jumping from lower to higher energy level, how much energy required? It is equal to delta E, and delta is equal to E2 minus E1. For this sample, delta is this one, delta is less, delta is less, this is more, energy gap is more, energy gap here is less. So as we know, E is equal to 1 by lambda. For higher energy, so this transition which require higher energy will be observed in a shorter wavelength. At the same time, this transition, that is electron transition from lower to higher energy, require less energy, will be observed at a longer wavelength. So this is observation. And what type of energy, what type of radiation is absorbed by sample? What type of radiation is absorbed by the sample? To what extent the radiation is absorbed is all depend on the structural feature of the sample. Is all depend on the structural feature of the sample. So by studying what type of light is absorbed by sample, to what extent is absorbed, it is possible to predict, to know the structure of molecule or to know the structure of sample. So this is what is the basic part of spectroscopy. This UV visible spectroscopy, also called electronic spectroscopy, right, which mainly concern with the electron transition from lower to higher. It is also called as, or this is coming under heading absorption spectroscopy. It is coming under heading, it is studied under heading absorption spectroscopy, which involve absorption of light by the molecule, get excited and will go from lower energy level to higher energy level. So it is absorption of radiation responsible for different transition called as absorption. But electron going from here to here, from lower to higher, at higher it is found to be unstable. So that charged body again try to come back to normal state. While doing so, it emits light. So that is also recorded. That part is studied under heading emission spectroscopy. It is emission spectroscopy. So in this introductory lecture, just I want to give some idea what is meaning of spectroscopy. Meaning of spectroscopy is, it is the interaction of different types of electromagnetic radiation with the sample. Sample will absorb some part of light, some part may not absorb. That absorbed light will, by the sample, will bring out the changes in the sample, and these changes are recorded in the form of a graph. Okay, and what type of light the sample is going to absorb is all depend on the structural feature of the sample. So by studying what type of light is absorbed by the sample, it is possible to give the correct structure of the sample, and it all depend on the energy gap. So, and we also know that those sample absorb different types of light, it is a lambda max. It is a one wavelength absorbed by the sample. It is a one wavelength absorbed by the sample to maximum extent is called as lambda max, and this lambda max only is responsible for different type of transition. This lambda max, it is a wavelength of maximum absorption, or the wavelength which is absorbed by the sample to maximum extent is only responsible for different transition in the sample. Okay, so this is what is the basic part of different spectroscopic method or UV visible spectroscopy, also called electronic spectroscopy, studying under heading absorption spectroscopy. Okay, in the next lecture we will see the principle of spectroscopy. Okay, thank you.